In this video, we will start our discussion of atomic structure, beginning with the electron. With the development of atomic theory, the exact nature of the atom became a subject of debate. Scientists like Dalton thought of them as small, indestructible spheres, objects that actually exist in the physical world. At the other extreme, scientists like Ernst Mach thought that the view of the atom as being a real physical object was a good mental picture to start working on other problems, but in actuality, atoms should be treated more as ethereal objects. So a question began to come up. What exactly is an atom? Is it a real object? And if so, does it have any type of internal structure? Einstein's theory of Brownian motion put to rest once and for all if atoms are real or not. The theory only worked by assuming that atoms and molecules exist. Key experiments that led to our further understanding of the atom included J.J. Thomson's cathode-ray experiment, the discovery of radioactivity, Millikan's oil drop experiment, Rutherford's gold foil experiment, and then Chadwick's experiments in which he discovered the neutron. In this video, we'll be discussing J.J. Thomson's cathode-ray experiment and Millikan's oil drop experiment, which led to insight into the nature of the electron. Presented here is a schematic of a cathode ray tube and a picture of an actual cathode ray tube. A cathode ray tube is a glass tube that's been evacuated of air. It has two metal plates, a negatively charged plate and a positively charged plate. Those charges are generated from a high voltage source. When you turn the voltage source on, what happens are so-called cathode rays stream from the negatively charged plate to the positively charged plate. The picture on the bottom shows cathode rays streaming from the negatively charged plate to the positively charged plate, which is a Maltese cross. The green that you see is from the cathode rays hitting the glass, causing some chemical on that glass to phosphoresce. It was found that these cathode rays are charged. If you put a magnet up to the cathode ray tube, you see the cathode rays deflect away from the magnet. J.J. Thomson was a British physicist who was working during the late 1800s and early 1900s. He spent years investigating the nature of cathode rays and was instrumental in demonstrating that they were small negatively charged particles, which are now called electrons. In another series of experiments, he used a modified cathode ray tube. This cathode ray tube possessed, in addition to the charged plates which generate the cathode rays, two additional charged plates that were separated by some distance, and a magnet in between those two charged plates. The cathode rays, when shot down through the center of those plates, would be attracted by the positively charged plate, deflecting them off of a straight trajectory. A magnetic field could be used to rebalance the particles back up into the center. By using those forces and working through the physics, Thomson was able to arrive at a charge-to-mass ratio of the electron. He determined that the charge-to-mass ratio of the electron is 1.76 times 10 to the 8 coulombs per gram. What this means is that either the charge of the electron is enormous or the mass of the electron is incredibly small. It took further experimentation to determine which is the case. In the early 1900s, Millikan performed his so-called oil drop experiment, which yielded the charge and the mass of the electron. In the experiment, a narrow stream of oil droplets fall down through a plate at the top of the apparatus. This plate has a positive charge. An additional plate at the bottom of the apparatus has a negative charge. The observer looks through a microscope. This microscope has a ruler on it so that the observer can measure both the size of the oil droplet and the velocity at which that oil droplet is falling. In addition, there's a source of ionizing radiation that is shot at these oil droplets, which generate positive and negative charges on those oil droplets. Oil droplets that don't have a charge will fall at some velocity. If the oil droplet obtains a positive charge, it'll be attracted towards the negative plate and drop faster. If an oil droplet gains a significant negative charge, it'll start to rise towards the positively charged plate. In some cases, oil droplets gain just enough charge that they don't fall or rise in the apparatus. The way in which this experiment was performed is that the observer would measure the size of the oil droplet. Knowing the density of oil, they could determine the mass of that oil droplet. They would then measure the velocity of the oil droplet and compare that velocity to what it should be if the oil droplets weren't charged. So the positively charged oil droplet dropping faster, the negatively charged oil droplet dropping slower, sometimes rising, sometimes staying still. From that, the charge on the oil droplet could be quantified in terms of some unit of coulombs. An assumption that was made is that charge comes in individual integer units. We're going to use some data to calculate the charge and the mass of the electron. So what we know from the Thompson experiment is the charge to mass ratio of the electron. We're going to look at 4 different oil droplets with 4 different charges, back out the fundamental charge, and then from that calculate the charge and the mass on the electron. What we're being asked is to solve for the charge and the mass of the electron. What we're given is the charge of 4 oil droplets, the charge to mass ratio of the electron, and the fact that charge is assumed to come in whole number integer units. There are multiple strategies that could be implemented to solve this problem. I'm just going to show you the one that works best for me. What we want to get is the charge of the electron and the mass of the electron. What we have is the charge to mass ratio of the electron. We're also given charge in the problem, so if we want to get mass, we should take the charge and multiply it by the inverse of the charge to mass ratio. Now what we have to do is calculate the charge. What we know is that we can get the charge of an electron by assuming that the charge on the oil droplets are going to become in multiples of the charge of one electron. If we take the ratios of the various charges, we can cancel out the charge of one electron, and we'll be left with simple ratios of whole numbers. We're going to use that ratio to back out the charge of one electron, use the charge to mass ratio, and back out the mass of the electron. We're now going to implement the strategy that we just devised. The first thing that we're going to do is we're going to cancel out the times 10 to the minus 19 term to simplify the math a little bit. We're going to take ratios of the charges of the oil droplets using the 3.2 times 10 to the minus 19 charge in all of the ratios. This will let us know if the 3.2 term is the fundamental charge of the electron. We find out it can't be because we don't have an integer values in both terms of the ratio of the 4.8 over 3.2. So we're going to divide that 3.2 term by 2, which would yield a 3 to 2 ratio. Going through, taking the calculated charge and the inverse of the charge to mass ratio of the electron, we determine the mass of the electron equal to 9.1 times 10 to the minus 28 grams. So we have both the mass and the charge of the electron. We arrived at an answer for the charge of an electron of minus 1.6 times 10 to the minus 19 coulombs and a mass of 9.1 times 10 to the minus 28 grams. For comparison, we can look at the proton, a charged particle that has the same magnitude of charge as the electron, just an opposite sign, but its mass is 1.7 times 10 to the minus 24 grams. So it's significantly more massive than the electron is. To determine if this answer is reasonable, we're going to make some estimates. We're going to estimate the charges as whole numbers 3, 5, 10, and 15. The reason that we did this is because these are easy to work with. Essentially what we did is canceled out the negative sign and canceled out the 10 to the minus 19. We can make a variety of ratios, the ratio of the smallest two being 3 to 5, which reduces to approximately 1 to 1.5. If we multiply by 2, we get rid of the 1.5, and we now have an integer value. This suggests that the smallest unit charge is the 3.2 divided by 2. So if we take the minus 3.2 times 10 to the minus 19, divide it by 2, we get negative 1.6 times 10 to the minus 19 coulombs. We can approximate the charge to mass ratio of the electron as 1.6 times 10 to the 8 coulombs per gram, which makes for a nice easy cancellation of units. What we therefore arrive at is 1 times 10 to the minus 27 grams for the mass of the electron, which is very close to 9.1 times 10 to the minus 28 grams. Some of the major takeaways are that the electron is a negatively charged particle that is much lighter than the proton, that the J.J. Thompson cathode-ray experiment yielded the charge to mass ratio of the electron, and that the Millikan oil drop experiment yielded the value of the fundamental charge of an electron and the mass of the electron. The experiment yielded the charge was used with Thomson's charge to mass ratio, and the mass of the electron was therefore obtained. In the next video, we're going to be exploring the properties of the nucleus of the atom. Some experiments can generate controversy decades after they were published. In the 1970s, the Millikan oil drop experiment became highly controversial. Someone started to look through the original data that Millikan had and compared it with what was published and noticed that there were a large number of values that never made it into the final manuscript, and therefore committed scientific fraud by not reporting everything. Other scientists further scrutinized his data and concluded that Millikan behaved scientifically ethically. What they determined was that if you kept those data points in, you would obtain the same answer. It's just that your statistics would get worse. They concluded that he was valid in eliminating those data points. My personal view is that Millikan behaved scientifically ethically, that he was on good statistical ground for eliminating those data points.